So there's some interested in something called photonic computing. And what this is instead of using electrons to do computation, we use light waves. And light waves are composed of photons. That's the particle composed of light waves. Light waves, like everything in quantum mechanics, but some stuff is more like this than other things, is both a matter, is both seen as matter and as a wave. Photons are the particle or wave. Photon is kind of the particle of light, and light is electromagnetic radiation. I think, and this photonic computing has some major advantages and disadvantages. One, compared to electronic computing, it could use a lot less power, and it would heat up the circuit a lot less. By heating up the circuit less, you cause less damage, you can run it at higher powers, and you don't have to worry about cooling and all that stuff or long-term damage, and it can last longer. Another major advantage is light is the fastest thing. Now, this speed of light thing kind of gets disrupted in when I say how fast it is, because light in a vacuum is the fastest thing. Now, light in a tube is not always the fastest. It slows down in water, in air, and the thicker the medium, the more it slows down. It's still significantly faster than most electrons. It also is faster in that transistors and everything, they use binary logic, ones and zeros. Stuff has to turn on and off like a switch. Light can turn on and off faster than electrons, which have to move a bunch of stuff around. And you don't have to worry about heat and stuff. Theoretically, this might even lead to more precise things because you don't have as much in between the 1 and 0, but not at the speeds we're doing it yet. And now it's less precise just due to technology constraints. It could lead to more multiplexing, where different wavelengths of light, so red light, green light, everything can do different computations in the same transistor, or stuff like that. It could lead to better ways of handling data that's transmitted by fiber optics or something like that, which is the fastest way of transmitting data right now. And you can compute the data in there instead of having it first turn into electricity and compute it, to speed up how data is transmitted a lot more, or do some pre-processing of data, which could help a huge amount. It might lead to better, more analog operations. So analog operations are operations that are not binary, not like the ones, zeros, or ands, or set mathematical operations, but more they take something and model it to get an output. So for example, if you want to figure out how two waves look like when you add it together, you can do it, convert the waves into a bunch of numbers, plot the numbers and add them together, or you can actually just make those two waves and look at it. You can have gears or something rotate to do math instead of doing it with ones and zeros and ands and ors. Well, some operations you can do analog with light waves, like Fourier transform, which is when you take a thing and break it down to multiple little waves. So you can take something like this and, that's just one wave, but like this can be approximated, this one big peak can approximate by two little waves like this, then a big wave like this, and so on and so on. It's better if I do a square, actually, where you could have one wave here, another wave here, then you could have a bigger wave here that part of it goes down over here. And they just add up and destruct to make any shape. You can do the opposite of a Fourier transform, where you can put the waves back together to make more complex. You can do certain integration where you find like area under the curve and stuff. Certain other mathematical operations you can do faster with built-in processes. Now, the problem with analog versus binary is that analog can work a lot better, more accurate, and faster, but it's not as flexible. Well, binary comes to digital computers, will be a better term for it, is more for, sorry, I should have said digital before, not binary. Digital is less, it can solve more wide range of problems. There's a lot of other potential, especially if we don't have to convert stuff back and forth between electricity and light waves, such as with using light cameras with it built in or something like that. However, there's many problems in that it's not as easy to integrate it with storage on the chip, because you don't have a good way of storing light waves as much. So, and a chip oftentimes has a lot of memory with RAM and stuff like that, which is a huge thing it needs, and this memory needs to be close by on off, and that's a significant thing that can slow down your computer. Right now, our components do not do digital operations with binary AND and ORs, not as well, and a lot bigger. There is a other problem with it, is that we don't have the big technology to make it as much yet. It is also now less precise and more finicky under most circumstances. So a ton of stuff that needs to be worked out, but it's probably going to be part of the revolution, and it's now getting rapidly better, almost at Moore's law speed, and sometimes faster, sometimes a little bit slower. Moore's law is about how fast computer chips were going, and for a long time they were improving at that rate, but now they're slowing down. But I want to highlight a separate use that I think will be very useful for them, and that is in outer space. Because I think there's a couple key things that in outer space, and also in nuclear reactors, and in some other environments, these chips could way outperform it if they were practically made. One is for power consumption. In space, power consumption becomes more and more important. And because you have solar cells and stuff like that, it becomes more limited, and the more solar cells, the more mass you need to bring up, and that makes the rockets big and everything. It also means that there's less power for other things. There's less chance if something goes wrong with the wiring it was. Also, the more power used, the more heat you generate, and it's hard to get rid of heat in outer space. And also heating, I have a third one later on for this stuff. So power becomes a lot more important in outer space. So having a low power device is better, and a photonic chip can use less than 10% of the energy, as Forbes reports and a bunch of other people, than a lot of modern day computing chips. And even though they're not as, in many ways, as precise or flexible, that's not a problem in a lot of outer space applications, because you're doing the same task over and over again. So some way you can make it an analog to make it overcome all those things, get rid of the digital aspect of it. Some of it you don't need as precise, because remember the power missions with the old clunky computers, or you don't need it, or you can get around with it with slightly turning off some of the energy efficiency, but making it more precise by having doing the same operation twice, or something along that lines could hugely help out. So another use for this is for things that just drones or anything that just needs to operate for long times, or things that might lose power a lot, or you need something that's just very reliable, but you don't need the most computation power. So this whole power requirement is a wonderful thing for many applications. And in those applications also, you never going to need as much power, if you're just tracking the sun. Another one is in a lot of places like space, nuclear power plants and stuff, there's a bunch of radiation. And radiation can really mess up your electronic systems. The way the radiation from our space can measure it is these are particle radiation, say of negative, plus or minus negative charges usually. These plus or minus negative charges can directly interfere with the memory, which we don't know how memory for all these ones work, so that's a different context, but they can directly interfere with the bits. So they can make an electron go off track. They can make it detect a charge of electron when it's not there because the radiation has it, or negate the electron charge and make it seem like the electron's not there. They can damage the silicon and stuff in the chip that's very sensitively doped and other components. When you're using a photon interacts much less with this, so it's much less likely to get disrupted. And it's also much easier sealed from radiation that disrupts photons compared to electric radiation. A second thing about the photon that aids it to it is the materials themselves get less damaged by radiation, or the damage is less important because they're not relying on very delicate electronic properties but more on refractive index, so less about the electrons and more about how dense and stuff the networks are. Another reason why this is better is because one way of getting rid of in electronics, getting rid of space disruption is using much more power or higher current, because then a slight amount of radiation doesn't impact the whole much electrons so much because you're overloading the system. But that means that the power saving from photonics could be even more great in space or nuclear applications. A final third thing that I want to say about how this technology could be a lot better is that they make a lot less heat and a lot less electrical disruptions and stuff, which means they can be put next to very sensitive instruments without bothering them as much, because heat can disrupt a lot of sensitive sensors. It makes light sensors themselves less sensitive. The hotter they are, it makes MRI sensors less sensitive. It can also disrupt very sensitive magnetic and electrical sensors. So by having this could mean the sensors and a variety of things, from MRIs to sensitive telescopes and stuff, could become more accurate or better handled. Well, thank you very much for listening. Please like and subscribe. It will help the channel out. I'm trying to reach 1,000 subscribers in a year and 4,000 watch hours, which is really hard, but with your help, I think I can do it. Also, if you have any ideas for future videos, comments, or suggestions, please leave them in the comment section below. Again, thank you very much. Goodbye.